All right, let's get into it. We're going to talk about one of the weirdest, most mind-bending ideas in all of physics. It's called quantum entanglement, and it's a concept that even Albert Einstein himself called spooky.
So what if I told you that two particles could be so deeply connected they act like a single entity, even if they're on opposite sides of the galaxy? I mean, think about that. You poke one here, and the other one, light years away, reacts instantly. Yeah, it sounds like something out of science fiction, but this is real. This is a core part of how our universe actually works.
And here's the kicker. The official definition says their quantum states can't be described independently. What that really means is you can't just talk about particle A without also talking about particle B. It's like they're not two separate things anymore. They've merged into one single inseparable system.
So let's dive into this spooky connection. Because let me tell you, it completely breaks our everyday intuition about how things should work. Okay, so picture this. You've got two entangled particles. We know their combined spin has to add up to 0. Now, you measure one of them, and bam, it's spin up. Well, because of that spooky connection, you know instantly, no hesitation, that the other particle, wherever it is, must be spin down. It's a perfect mirror image every single time, no exceptions. And you might be thinking, this is all just theoretical, right? Nope. Scientists do this for real, in labs, every day. One of the coolest ways they do it is by shooting a laser through a special kind of crystal. The crystal takes one photon and splits it into two new photons. And these two new photons, well, they're born entangled. They're linked from the very moment of their creation.
Okay, this is probably the most important part to get your head around. What's the real difference here? Let's start with something normal. Think about a pair of mismatched socks. You put one in a box and send it to your friend in another country. When you open your box and see a pink sock, you instantly know your friend doesn't have the pink one, right? But that's not spooky. The color of the sock was always there, decided from the start. Now for the quantum version. With entanglement, it's totally different. The particles don't have a predetermined property like spin up or spin down. It's like they're in a fuzzy, undecided state. The moment you measure one and it chooses to be spin up, the other one, across the universe, instantly chooses to be spin down. The property isn't just revealed, it's created for both at the exact same time. So this whole instantaneous thing, it didn't sit right with a lot of people. In fact, it really, really bothered one of the most famous scientists who ever lived. And this objection kicked off one of the greatest debates in the history of physics.
Yep, we're talking about Albert Einstein. Back in 1935, he and a couple of colleagues, Podolsky and Rosen, dropped a bombshell. They published this paper which basically said, hey everyone, this quantum mechanics theory, it's got a hole in it. It's incomplete. They just couldn't stomach this idea of an instantaneous connection, calling it a paradox.
And this is where we get that legendary phrase. Einstein dismissed the whole idea as spookhafte Fernwirkung, which, when you translate it, means spooky action at a distance. You can just feel his disbelief in those words, right? The idea that measuring something here could have an immediate effect on something way over there, it just broke the rules of his universe.
Einstein's whole argument rested on two big ideas that honestly just feel like common sense. The first is locality. It's the simple rule that nothing can travel faster than light, no instant messages across the cosmos. The second is realism. This is the idea that a particle, has real properties like its position or spin, even if we're not looking at it. So he figured there must be some hidden variables, some secret instructions the particles had all along that we just weren't smart enough to see yet. To him, that was the only way to explain the correlations without breaking the speed of light.
And for a long, long time, that's where things stood. It was basically a philosophical argument. Team Einstein versus Team Quantum. But then, decades later, a physicist came along and said, you know what? We can actually test this. We can settle the debate once and for all.
And that physicist's name was John S. Bell. In 1964, he did something absolutely brilliant. He came up with a theorem, a mathematical test that could distinguish between Einstein's worldview with its hidden variables and the weird, spooky predictions of quantum mechanics.
What he came up with is now called Bell's inequality. And you can think of it like this. It's a mathematical line in the sand. Bell showed that if Einstein was right, if the world was governed by local realism and hidden variables, then the correlations between the particles could only be so strong. They could never, ever cross that line. But if quantum mechanics was right, the correlations would be stronger. They would break the inequality, they would cross that line. Suddenly, the debate wasn't philosophy anymore. It was about running an experiment and seeing which side of the line the results fell on. So, the stage was set. The test was designed. All that was left to do was run the experiment. So what happened? Who was right? Well, it turns out, reality is even weirder than we thought.
The first real experiment to test this was in 1972 by Friedman and Clauser. And the results? They broke Bell's inequality. The universe crossed the line. Then, in 1982, a physicist named Alain Aspect conducted an even better, more rigorous experiment that closed off some of the potential loopholes. The result was the same. Again and again, the spooky connection held up. And this work was so foundational, so important, that in 2022, Aspect, Clauser, and another pioneer, Anton Zeilinger, were awarded the Nobel Prize in Physics. They had finally proven Einstein wrong.
So after decades and decades of experiments, the verdict is in, and it is crystal clear. Bell's inequality is violated every single time. Einstein's spooky action at a distance is real. Our universe is fundamentally non-local. What happens here can instantly affect what happens over there. It's a tough pill to swallow, but it's the reality we live in.
But here's the amazing part. What was once seen as a paradox, a flaw in the theory, is now being harnessed as one of the most powerful tools we've ever discovered. Scientists are now asking, how can we use this spookiness to build the technology of the future?
And this isn't just a small thing. Entanglement is the fundamental resource behind a whole new technological revolution. We're talking about quantum computers, which could solve problems that are impossible for even the biggest supercomputers today. We're talking about quantum cryptography, creating communication channels that are literally unhackable. And yes, it even lays the groundwork for things like quantum teleportation and superdense coding, which sound like sci-fi but are real concepts being developed right now.
Check this out. This is a mind bender called entanglement swapping. You have two separate pairs of entangled particles. Let's say A is linked to B and C is linked to D. Now, you take B and C, the two middle particles that have never met, and you do a special measurement on them together. The instant you do that, particles A and D, which have never interacted and could be miles apart, suddenly become entangled with each other. It's like a long-distance relationship set up by their friends. This is a critical building block for creating a future quantum internet.
So really, the best way to think about this now is that entanglement is a kind of resource. Just like we think of energy as a resource that lets us do work, like moving a car, scientists now see entanglement as a resource that lets them do incredible new things with information and computation.
And you know, it wasn't just Einstein who was obsessed with this. Erwin Schrödinger, of Schrödinger's cat fame, totally got how important it was way back in 1935. He wrote that entanglement isn't just some weird feature of quantum mechanics. He called it the characteristic trait. It's the one thing that truly separates the quantum world from our everyday classical world. And that just leaves us with one final, kind of profound thought to chew on. If these entangled particles really are an inseparable whole, connected instantly across any distance, then what does that say about space itself? Where does one particle truly end and the other begin? It really makes you question the very nature of what it means to be separate.